Welcome to Zaption Tour 5.2, Direct Variation. There's 8 boxes. The first thing I want to do is do a little introduction with you. So take a look at this picture. It says the diagram shows how long it takes to hear thunder after you see lightning, okay? Don't worry about this part right here. I just want you to take a look at the picture. So here's somebody over here, and they're listening. And then here's somebody over here, and they're listening. And they see lightning right about here. And this person is exactly 2 miles away, and this person is exactly 3 miles away. And it takes this person 10 seconds to hear the thunder, and it takes this person 15 seconds to hear the thunder. This introduction is an example of what's called direct variation. And we're going to talk about that in this lesson. Here is the essential understanding. It says this, it's an if-then statement. If the ratio of two variables is constant, then the variables have a specific relationship called direct variation. And the way that we're going to represent direct variation is by this. Y is equal to some k times x. So therefore, we can always solve for k. If I call k my constant of a variation, my constant, because after all, it has to be constant. If I solve for k, I would get that k is equal to y divided by x. If I just divide both sides of this equation by x, that's how I got that. So notice that here is the ratio, right? The ratio between two variables, between my variable y and between my variable x. You'll also notice that this looks really similar to slope because we have y divided by x. It is very similar to slope, but we're calling it constant of variation in this particular lesson. Box number 1 is an example. It says identify direct variation. I have two equations here. There's the one on the left, which I'm calling A, and one on the right, which I'm calling B. The one on the left is indeed direct variation. The one on the right is not, and here is how you can tell the difference. What you're going to do is you're going to solve these for y. So I'm going to divide by 7, I'm going to divide by 7, and I'm going to see that y is equal to 2/7 of x. That's what that says. 2x divided by 7 is the same thing as 2/7 of x. Therefore, I can see that this value, 2/7, this is my k, this is my constant of variation, because the ratio between two variables is constant. The ratio between x and y is 2/7. Now take a look at this one over here. Again, I want to solve for y to see if I have direct variation. So I'm going to move the 4x over to the other side of the equation. Okay, this is going to give me 3y is now equal to negative 4x plus 8. And then I'm going to divide both sides by 3 to cancel out everywhere. Okay, so I end up with y is now equal to negative 4/3 x plus 8/3. So you can see the difference between the two, right? The difference between this one, or part B and part A, is the fact that I have this extra constant term on the end, all right? This part right here is what makes it not direct variation. If that wasn't there, then I would have only y equals negative 4/3 x, and then it would be direct variation. But because I have this constant 8/3 on the end, I do not have direct variation. Okay, here's a U-try. So does 4x plus 5y equals 0 represent direct variation? Yes or no? If it does, can you tell me the constant of variation? Hopefully you got the right answer, but if not, here's how you do it. First, you solve for y. So I have 4x plus 5y is equal to 0. So then I would have 5y is equal to negative 4x, and then I would divide by 5, and divide by 5, and I would see that y is equal to negative 4/5 x. This is in the form of y equals kx, and therefore the k in this case would be negative 4/3, so my constant of variation would be negative 4/5. I'm sorry, I think I said just 4/3. So negative 4/5. So yes, this does represent direct variation, and the constant of variation is negative 4/5. Box number 3 is an example of writing direct variation equations. It says, suppose that y varies directly with x. So whenever you see this statement, everybody, whenever you see, suppose that y varies directly with x, we can automatically write down this, y is equal to k times x. That's the definition, and that's what that statement means. Then we read on and says that when y is equal to 35, okay, let me move this up a little bit. So when y is equal to 35, we know that the x value is equal to 5. So it's equal to k times 5. Then it says, what is the value of y when x is equal to 9? So this first statement here, when y is 35, x is equal to 5, allows me to write down plugging in 35 for y and 5 for x. And therefore, if I just solve by, if I divide both sides by 5, I will get that the k value is worth 35 divided by 5 is worth 8. Or 7, excuse me, I was in the wrong spot. Is worth 7, because 7 times 5 is 35. So now I take this information and I'm allowed to say, okay, every y is worth 7 of my x's. That's what that means for direct variation, because the k is 7. Then it says, what is the value of y when x is equal to 9? So I plug in, okay, 7 times 9, and I want to know the y value. 7 times 9 gives me the 63. So therefore, y would be 63 when x is equal to 9, assuming that y varies directly with x, and that when y is 35, x is 5. So you're going to see problems like this. Okay, here's one for you to try on your own. It says, suppose that y varies directly with x. So here's that statement again. It's a very famous statement. Suppose that y varies directly with x. What can you then write down? It says, when y is 10, x is negative 2. And then what is the value of y when x is negative 15? So look back to box 3, see if you can figure this out. Okay, I hope you guys got this one correct, but if not, here's how it goes. So suppose that y varies directly with x. I know that I can write down y is equal to k times x. Then it says when y is equal to 10, so 10 is equal to k times negative 2. I can then easily just solve for k by dividing by negative 2, and I would get that k is equal to 10 divided by negative 2 is worth negative 5. So therefore, I can write down, okay, y is equal to negative 5x. Every y is worth negative 5x. Then it says, what is the value of y when x is worth negative 15? So I'd say y is equal to negative 5 times a negative 15. Multiplying these two together, you get that y is worth 75, and it will be positive. So there is the answer. Box number 5 is all about graphs of direct variation. I've switched over to a different program here. I have 4 graphs, or 4 equations that I'm going to graph for you, A, B, and C. And then I have D over here on the right. You can see that A, B, and C, they all have direct variation form, meaning they all have the form of y equals k times x. So I'm going to graph all 3 of these at once for you like this and put them onto the graph. And there they are there. That's a pretty cool, beautiful graph. So taking a look at this picture right here, okay, is there anything that you notice that happens that is common between all 3 of these lines right now? Okay, hopefully you noticed something about all 3 of those lines. If you did not notice something about all 3 of those lines, I'm going to graph this line for you now, graph D. This graph is not direct variation. I'm going to graph it for you right now. So there you go. Can you see why? What's different between the black line versus the red, the green, and the blue lines? Okay, now I've added equation E. What do you think this one's going to be, direct variation or not? You'd be absolutely correct. This is not representative of direct variation. And here's the graph of graph E. And you can see right away that it does not go through the origin. And that's the key. It does not pass through the origin. So all graphs of direct variation must pass through the origin. Okay, here's box number 6. I have 3 graphs for you, A, B, and C. Which graphs represent direct variation? Hopefully you picked B and C only, okay? B and C represent direct variation, A does not. The reason is because both B and graph C pass through the origin located at 0, 0, located at 0, 0, whereas this graph does not pass through the origin. It passes at 0, 2. So this one does not represent direct variation. Only B and C represent direct variation. Box number 7 is all about how to write direct variation from a table. I have two tables here for you. Table A represents direct variation. I'm telling you now that it does. Table B does not represent direct variation, and I want to show you how this works. Remember, we have to have the ratio of y over x, and that has to be a constant value k. This is the definition of direct variation for us. So here's what we're going to do. We're going to take every y value and divide it by every x value. So I'm going to take 6 divided by 4, and I'm going to get 1.5. I'm going to take 12 and divide it by 8, divided by 8, and I'm going to get, again, 1.5. I'm going to take 15 and divide it by 10, and divide it by 10, and I'm going to get 1.5. So because I get 1.5 every single time, the answer is yes, it does represent direct variation, and guess what? 1.5 represents the k value, the constant of variation. Now take a look at table B. You're going to see that this is not going to work out for us. If I take 3.2 and divide it by -2, I would get a value of -1.6. But if I take 2.4 and divide it by a value of 1, I would get a value of 2.4. And then just to be thorough, if I took 1.6 and divided it by 4, I would get a value of 0.4. So because none of these match, it does not represent direct variation. Okay, last box, you try. Does the table represent direct variation? If it does, tell me the constant of variation. Hopefully you got yes is the right answer, and here's why. If I take 2.25 and I divide it by -3, I get -0.75. If I take -0.75 and I divide it by 1, I get -0.75. If I take -3 and divide it by 4, I get a -0.75. Therefore, this is constant, and my k value would be -0.75.